In this lesson, we're going to talk about two laws that really tie all the others together, ideal and Dalton's law. First, I'd like to introduce the concept of the molar volume of a gas. Remember, gas particles have both indefinite shape and indefinite volume. But as it turns out, if we've got standard atmospheric pressure and standard temperature, if you have a certain number of particles of gas, without regard to which types of particles you have, it could be a mole of pure oxygen, it could be a mole of pure argon, it could be half oxygen, half argon, any combination. As long as you have 1 mole of those particles, it will occupy exactly 22.4 liters of space at standard temperature and pressure. We abbreviate that STP. Standard pressure is either 760 millimeters of mercury or 1 atmosphere. Standard temperature, 0 degrees Celsius or 273 degrees Kelvin. We put that all together, there's a law that summarizes all of the variables. Up till now, we've only considered 2 variables at a time: pressure and volume in the case of Boyle's law, volume and temperature in the case of Charles, pressure and temperature in the case of Gay-Lussac's law, and volume and number of moles in the case of Avogadro's law. But what if we put that all together for any gas in any one given set of conditions? Its pressure times its volume is equal to the number of moles that it has times something called the universal gas constant, which is abbreviated R, times temperature. R is a different one, or different letter that we see here, and it stands for universal gas constant. And you can either memorize or look up several different values of R for the different units of pressure and volume and temperature you put in, or you can say, here's one given value of R, and you should convert your pressure, your volume, and temperature into units that match this. I think that latter approach is better, and so that's the way I'd like to teach it. R is equal to 0.082, and the units are incredibly complex here. Liters times atmospheres, all divided by moles times degrees Kelvin. Liters, of course, is the unit that your volume would need to be in order to use this law. Pressure needs to be in atmospheres. Temperature needs to be in Kelvin. And there's no other unit for number of particles besides moles, so that's an automatic one. When using the ideal gas law, these are the units that you must convert into. There's another law that I'd like to talk about. It's called Dalton's law. Dalton said, if there are different types of gases in a container, each gas exerts a pressure independently of the others. Independently. Remember that Montana example in the previous lesson, or two lessons ago? If you double or triple or even quadruple the population of Montana, it's still going to feel largely empty. Well, it's kind of like that with gases. You can double, triple, or quadruple the number of particles, and it's still that those particles will not interfere with each other because of the tremendous amount of space in between them. So Dalton says, listen, I can calculate the pressure that each gas would exert on its own, and I'm going to call that the partial pressure. And according to Dalton's law, if you add up the partial pressures for all of the different types of gases that you have in a sample, you'll arrive at the total pressure. So it's a very simple mathematical formula. If there's 2 types of gases, let's say, in a sample, then you would add together partial pressure of gas 1 and the partial pressure of gas 2 to get the total. If there's 3, then you would add partial pressure of gas 3. If there's 4, you would add partial pressure of gas 4. If there's 20, you would keep adding until you've reached all of the gas samples or gas types that are in that sample. Since in a gas, we presume that the particles are not interacting, it doesn't matter what type of particles we have. All that matters is the number of particles. Here's a pressure or a picture that shows some of these relationships. In the left side, we've got half of a mole of hydrogen. It's kept at 5 liters and 20 degrees Celsius. Under those conditions, the hydrogen alone exerts a pressure of 2.4 atmospheres. In the picture in the middle, 5 liters and 20 degrees Celsius, we have 1.25 moles of helium. Under those conditions, the helium exerts 6 atmospheres of pressure. What Dalton is saying is you can overlay the hydrogen particles onto the helium particles, and still you would have largely empty space. Now, the picture on the right is showing the 2 gas particles overlaid on top of each other, but it's not to scale. Most of these particles are much, much, much smaller in reality than what they're being shown here. But he's saying that if you overlay those two, the pressure that the helium exerts, which was 6 atmospheres, plus the pressure that the hydrogen exerts, which is 2.4, will be the total pressure of 8.4. Let's try a sample problem that puts both the ideal gas law and Dalton's law together. If 1 mole of helium and 0.25 moles of oxygen gas are placed in a 5-liter vessel at 65 degrees Celsius, what will be the partial pressure of each gas and the total pressure of the vessel? We're going to apply the ideal gas law separately to each of the 2 gases. We're going to use PV equals nRT, both for the helium, and then we'll go back and use PV equals nRT for the oxygen. In both cases, we're going to solve for the pressure. So the pressure is not known at present, but we do know that both of these gases are in a 5-liter vessel. They're in the same 5-liter vessel. They told us in the problem that we have 1 mole of helium. So where we have N for the helium equation, I'm going to put 1.0 moles. The value of R, it was that goofy thing, 0.082, and that will never change. That's a constant, regardless of which gas you're considering. And it has funny units, liters, atmospheres, over moles times degrees Kelvin. And the beautiful thing about that is it tells you what units everything else needs to be in, which is kind of a nice reminder. If we have 65 degrees Celsius, and we know that we need to convert that into Kelvin, we're going to add 273 to it. So 65 Celsius plus 273 gives us 338 degrees Kelvin. If you follow the units within this equation, you'll notice that liters will cross out with the liters in the universal gas constant. Moles crosses out. Degrees Kelvin crosses out. The only thing that doesn't cross out is the unit for the pressure that we're going to solve for, atmospheres. The pressure for the helium, and I'll put HE below that, helium's chemical symbol, in this case works out to be 5.54 atmospheres. To get that, I took 1 times 0.082 times 338 and divided all of that by 5. Now let's do that again for the oxygen. The volume is the same as for the helium because it's in the same container. The number of moles is different. They told us that we have 0.025 moles. So where it says N, I'm putting 0.025. The gas constant will be the same as before, 0.082. And those goofy units, you should pay attention to those. Those are important. Liters, atmospheres over moles times degrees Kelvin. And the oxygen was kept at the same temperature that the helium was. So if you figured out 65 Celsius is 338 Kelvin, you can just use that same value again. On my calculator, I'm typing 0.025, I'm sorry, 0.25 times 0.082 times 338, and I'm dividing that by 5 liters. And when I crunch all those numbers, I get approximately 1.38 atmospheres. Okay, so we applied the ideal gas law for the helium and for the oxygen. Now for the Dalton's law piece. In this sample, there are 2 types of gases. They don't mention any other type of gas besides the hydrogen and the helium. So Dalton says, if you want the total pressure and you know the partial pressures of each individual gas, simply add them together and you get your total. This one's a cinch to apply, right? You just add the 2 numbers, 5.54 plus 1.38. And we get 6.39 for our total pressure. Great work. Good luck on the homework.